Hello, ladies and gentlemen. Welcome back. Let's go ahead and look at Chapter 3, Part 2. Now, this should be pretty quick. I just want to go over a few things and then go through another example with you, and then that's it. All right, so if you look at this picture, okay, let's study this picture. If you look at the red curve, the red normal curve, and the dashed line for that normal curve, okay, that's like the population distribution. Now, normally we don't know, okay, realistically, we don't know what the whole distribution of the population is. But we're going to say that the population distribution is normal, okay? Remember, if it's normal, then any sample that you draw, okay, of whatever size, if you draw enough of those samples, it's also going to be normal. Now, the population distribution, ladies and gentlemen, is always more variable than sampling. Because think about it, the population distribution contains the extreme lows to the extreme highs. It contains everything, so it's more spread out. But as you sample, and the size of your sample, again, this is the central limit theorem into play here, the sides start to draw in. It gets less variable, and this is a good picture. If you look at the next curve, that's like a sample size of 4. Okay, the sides got drawn in. It's a little bit more of a peak. Okay, then the next one you see the sample size is 16. The sides are drawn in a little further. It's a little bit higher to peak. And then 64, boy, that really draws in the sides and you've got your peak. And you'll notice that every single time when we do that, whether we're talking about a proportion or we're talking about a mean, it's always going to be in the center. If you're doing the sampling appropriately, you will find the true population mean or population proportion, depending upon which one we're doing. All right? And notice that standard deviation keeps getting smaller and smaller and smaller as the sample size goes up. If you think about the standard deviation for a proportion, ladies and gentlemen, the square root of p times 1 minus p divided by the sample size, well, think about it. As you divide, as that number, that denominator goes up, obviously it's got to bring in, it's got to make the standard deviation smaller. Same thing if we're talking about the standard deviation of a mean, okay, of x bar. Okay, I'll put a p hat on that one because that's what it is. It's for a sample proportion and then a sample mean. Okay, here's the standard deviation. That would be the standard deviation divided by the square root of n, right? Because as n goes up, it's going to get smaller and smaller and smaller. It's going to draw in that side, in those sides, all right? Okay, so let's look at this example. Let's move on. So the distribution of actual weights of 8-ounce chocolate bars. I do love chocolate, ladies and gentlemen. All right? 8-ounce chocolate bars produced by a certain machine is normal with mean 8.1 ounces. Okay, it's telling us, oh, first of all, this is really important. It's telling us it's normal. Okay, that is pretty important. You really got to read these problems carefully and look for key things. It's telling us it's normal. The mean is 8.1 ounces and the standard deviation is 0.1 ounces. Okay, I'm going to be craving chocolate all day today. All right, company managers do not want the weight of the chocolate bar to fall below 7.85 ounces. Okay, they do not want that to happen for fear that consumers will complain. Well, yeah, if I don't get what I want in my chocolate, I'm going to complain. Now, it says that they're supposed to be 8 ounces, right? But they don't want them to fall below 7.85. All right, find the probability that the weight of a randomly selected candy bar, that means n is 1, uno, is less than 7.85 ounces. All right, Now remember, notation is everything here. Well, I shouldn't say everything, but notation is important. So we're going to write the probability. All right. And imagine that we defined X already. X is going to be the weight of the candy bar, right? So X is less than 7.85. Okay, I'm just going to stick with less than because it said below 7.85. But putting the equal to on it isn't going to matter. Okay. All right. So now I'm going to go ahead and I want to convert that to a z-score. And then I will find the answer. All right, here we go. So off to the side, I'm going to go z equals. All right, well, it's 7.85 minus the 8 ounces divided by the standard deviation is 0.1 ounce. And normally I would divide by the square root of the sample size, but in this case it's 1. So you really don't need to put the square root of 1 underneath that because it's not going to affect it. So I'm just going to back out and just leave it as a 1 there. All right, and when I do that, ladies and gentlemen, I'm going to get a z-score of negative 2.5. Let me double check to make sure I got that right. 7.85 minus 8. Divide that by 0.1. Yep. Hold on here. That doesn't look quite right. It looks like 1.5 to me. Hold on here, Mr. Ellering. Let's triple check this. Okay, hold on. 7.85 minus 8. I do have the ounces right, correct? Yeah, 8 ounces. Okay, whew, I was a little worried there. And then I'm going to divide that by 0.1. All right, so I see. Good thing I double and triple checked. It's negative 1.5, ladies and gentlemen. All right, so the z-score is that. Now again, I recommend drawing pictures. So negative 1.5 is here, and we're wanting to know what is the probability. All right, so again, I'll pull up my the calculator and go through this again. So again, one more time, we're going to go second bars. We're going to go ahead and pick number 2. Our lower bound, since it's shaded to the left, our lower bound is going to be negative 100. Our upper bound is going to be the negative 1.5. Okay, we're going to go ahead and go down and paste that in. And looks like we get 0.0668. All right, 0.0668. So the probability, I'm going to type this out. Let me make that a little bit larger here. All right, so the probability that a selected, remember, use your question to help answer it. The probability that a selected candy bar is less than 7.85, whoops, that 7.85 ounces is about 7%, or is, well, yeah, no, let's do it like this, is about, I'm still going to put about 6.68%. If you want to leave it as a decimal, leave it as a decimal. Okay, so that probability is about 6.68% of that happening. Okay, so if you think about it, roughly 7 out of 100 times that will happen. So if they make 100 candy bars, okay, so you don't need to write this part, but think about this. So out of 100 of these chocolate bars, can't type. Out of 100 candy bars, 7, about 7 would be less than the 7.85 ounces. Whoops, about would. I'm filming this really, or making this really early in the morning if you look at the timestamp, all right? So out of 100 candy bars, about 7 would be less than 7.85 ounces. All right, so that's what that's telling us. All right, let's keep going here. Now, let's say 4 candy bars are selected at random and their mean weight X bar is computed. Describe the center, shape, and spread of the sample distribution. All right, well, the center, ladies and gentlemen, that's the mean. So the mean of our sample distribution should be the mean of the original problem, 8 ounces. Okay, that's not going to change. That's not going to change. Okay, I'm going to go to the spread next. The spread, which is the standard deviation, ladies and gentlemen. So the spread in this problem is going to be the 0.1 divided by the square root of 4. Okay, actually, let me back that up and just put the general first. So it's going to be the standard deviation divided by the square root of the sample size. So that's going to be 0.1 divided by the square root of 4. And that's going to be 0.1 divided by 2. And let me double check this. 0.1 divided by 2 is 0.05. So that's the spread, ladies and gentlemen. Now, the shape of the distribution, ladies and gentlemen, okay, let me go back to this really quick, and let me pull this down. So this is the extra notes I have for you. So it says right here, if the population is normal, the sample distribution, regardless of sample size, will be normal. Well, ladies and gentlemen, the original problem says, let me go back up, the original problem says that it's normal. It says it in the problem, okay? Now, if it doesn't say it in the problem, then we have problems, all right? That's when we're gonna, we don't know what the shape is gonna look like. If we don't know that, if it doesn't say it's normal, then we'd have to say, hey, I don't know what the shape is gonna look like because it doesn't state that it's normal. But since this one does state that it's normal, we can simply say the following, okay? The shape of the sampling distribution is normal since the parent population is normal. Okay, the parent population is the whole population, okay? So that's how I know the center. Okay, the center again is the mean. The standard deviation is the standard deviation divided by the sample, the square root of the sample size. And the shape is going to also be normal because the parent population is normal. All right, let's keep going. We're almost done. Promised this one would be quite a bit shorter, so I'm going to try to keep that promise. All right. The distribution of, okay, same thing. So now find the probability that the mean weight of the 4 candy bars is less than 7.85 ounces. All right, so, whoops, I didn't want that yet. So we're going to go ahead and set it up again. We're going to go PX. Again, make sure you define X. If this was an AP test, you'd need to make sure you write out what does X represent. So it represents the size of the candy bar, right? The weight, the ounces of the candy bar. All right, is less than 7.85 equals, we're going to convert that to a z-score. Now, obviously, the z-score is not going to be the same as number 1 because of the sample size. All right, so Here we go. Z equals the 7.85 minus the 8 divided by, now we already found the standard deviation right here, so I don't need to do this part again. So the standard deviation of a sample of 4 is 0.05. All right, so we're going to go ahead and put 0.05 down here. All right, so that's going to be 0.15 divided by 0.05. And since I made a mistake on the first one at the beginning, I'm going to double check this one. 0.15 divided by 0.05, that's a 3. Wow, okay, now that's really large, right? Think about the normal curve again. 3 standard deviations all the way. Oh, it's negative. See, I almost goofed again. It's -3. Okay, and -3 is way down here, and that's just that little teeny bit of the tail, right? It's that little teeny, let me put that negative on that one, the little bitty part of that tail. So when I do this, okay, there's not much area there, folks. If I make my, oops, I want this to be, hold on, why did it do that? I must be leaning against the thing here. All right, so I'm going to put my -100 again because it's shaded to the right. And I'm going to put my -3 here. And I'm going to paste that in. And it's going to be really small, 0.0013. 0.0013. So the probability of this happening, ladies and gentlemen, is less than 1%. So the chance of this happening is pretty small. Okay, let me move this down so I can type down here. All right, so again, using the problem, ladies and gentlemen, the probability that the sample of 4 candy bars is less than 7.85 ounces is less than 1%. It is very unlikely to happen. If it did happen, now I want you to start thinking about this. If it did happen, then there's something wrong with the machine. The probability is so small, it should not happen. But if you did pick 4 candy bars and you did get that result that it's less than 7.85 ounces, then you're going to go, uh-oh, something's wrong with the machine, okay? So it's very unlikely to happen. In fact, if I go a little bit further with this, look at your place value, tenths, hundreds, thousands, 10,000s. This is saying with that 0.0013, this would happen about 13 out of 10,000 candy bars. It's not really going to happen. It might happen 13 out of 10,000 times. Not a big deal. Customers are probably never going to notice. Okay, but if you did pick that sample randomly and you did get that less than 7.85 ounces, that's going to be a big red alert. That's going to be our inference, ladies and gentlemen, in the second part of the book. All right, let's wrap this up. I'm already at 19 minutes. My goodness. All right, so this one. Would your answers to 1, 2, or 3 be affected if the weights of the chocolate bars were distinctly non-normal? Well, yes to all of them, folks. Well, I shouldn't say yes to all of them. Yes to number 1 and 3, because it says here, if the population is not normal and the sample is small, the sampling distribution will be similar to the shape of the parent population. This is bad. that means you cannot rely on your result. Okay, so here we go. So I'm going to go ahead and do this. So if the parent population is not normal, question 1 and 3 would definitely, make sure I spell definitely right, definitely be affected. The sample size is too small. Now, question 2, the center and spread of the sampling distribution would not change. Okay, doesn't matter what the population distribution looks like. The center and the spread of the sampling distribution, that's not going to change. Okay, so the mean is still going to be the 8 ounces. The mean is still going to be the 8 ounces. So let me back up real quick. So the mean is still going to be 8 ounces. And the spread, the standard deviation, is still going to be 0.05. So just because the population is not normal, the center and the spread of the sampling distribution would not change. Okay, they're not going to change. Okay, however, the shape of the sample distribution would change. Because you don't, again, if it's not normal and it's really small, you don't know what your shape's really going to look like. It's gonna match more of the parent function. Okay, let me see if I have that on these extra notes. Nope, I don't have that on there. Okay, but I think I talked about it in the last video. All right, so go back, think about that, read the question again, think about what I typed there. Okay, I want to cut that off here. I'm just over 23 minutes. All right, ladies and gentlemen, see you soon.